Hi everyone, my name is Ray. I'm from the Ohio State University. In this video, we present our paper, DocFlow, a visual analytic system for question-based document retrieval and categorization. Nowadays, clinical decisions rely on systematic reviews with up-to-date research evidence to support the evidence-based practice. With the growing size of literature, human-in-the-loop retrieval systems are becoming more and more important to assist the clinicians with this process. Such a system usually comes with both query algorithm and visual analytics to facilitate understanding of the corpus and the retrieval. Despite the importance, we find that there are still three major challenges that make the existing approaches become gradually untenable. First, most of the existing systems only recommend documents that are semantically similar to the query. However, these documents may not contain the answer to the clinician's question. Consequently, they still have to take a long time to review many irrelevant documents. Second, clinicians often need to categorize documents from different perspectives on the fly, like population being studied or treatment being used. This means existing methods which generate a static clustering result based on the entire context can barely provide satisfying results. Third, in real world, information seeking is usually an iterative process that involves a continuous refinement of search strategies. So clinicians can quickly lose track of how the resulting documents are retrieved during a multi-step query and exploration. To better understand the domain requirements and propose efficient solutions, we conducted a formative study with domain experts and derived a set of requirements. First, our domain experts indicate that retrieval algorithms should allow clinicians to use both the natural languages and the question format phrases to perform the retrieval. Second, in a systematic review, information that clinicians are interested in should be recognized from the document first and then used to categorize them for further analysis. So this requires our algorithm to categorize documents on the fly based on user-designed perspectives. Third, all experts express the need for effective visualization and interactions to facilitate the exploration and keep track of the document retrieval process. Based on the requirements, we present DocFlow, a component-based visual analytic system that supports document retrieval and categorization with natural language questions. In the following sections, we will first introduce our retrieval and categorization model and then dive into the design of the DocFlow. The query-based retrieval is essentially a model that takes a query and a collection of documents as input and output candidate documents. To achieve this, the model first embeds questions and each of the document into a vector representation and then perform search based on vector similarity. Considering that questions and documents usually have different syntactic features, so we apply a dual encoder to encode question and document separately. Since we're targeting on biomedical literature, both of the encoders here are actually bellbird encoders. Use dual encoder structure makes the document embedding generation independent from the query. This gives us a benefit that document embedding only need to generate once during the data preparation, and then we can achieve real-time inference. However, because of this independent generation of the document embeddings, we consider they are more likely to reflect the overall semantics. Thus, before conducting similarity-based search, we apply an attention layer to adjust the document's embedding to reflect the focus of the query. During the implementation, attention layer is implemented just as a linear layer. To achieve the desired effect, we train the dual encoder-based model such that given the query, a positive documents which are considered to contain the answer to it, and n-negative documents which are irrelevant to it, we will likely to have the effect that embedding similarity between Q and the positive documents to be significantly higher than the similarity between the negative pairs. We use the info-NCE loss to train the model and use a combination of multiple question answering datasets as our training data. Next, we introduce our query-based categorization model. This categorization model is a combination of answer extraction and answer categorization. So the idea behind such a design is that we want to categorize documents based on their answer to the user's query. Thus, give a corpus and a query, the model first extracts answer from each of the document and then categorize them based on the embedding of the answer tokens. However, considering that not all documents may contain the answer, we need to filter out the irrelevant ones to ensure the quality of the categorization result. Therefore, we apply a query-based retrieval operation before every categorization to filter out the irrelevant papers. Next, we introduce the design of the DocFlow. So the essential idea behind the design of the system is that information seeking is an iterative process consisting of many retrieval, categorization, and visual analysis steps. To ensure the system can satisfy this need, we concrete the idea into 3 design principles. First, considering the complexity and commonality of a typical document retrieval process, DocFlow should allow users to build customized retrieval pipeline with composable and reusable components. Second, DocFlow should support intuitive user interactions for composing a retrieval pipeline with components and links. Third, the system should support saving and loading constructed pipeline to reproduce the information seeking process. Based on these requirements, the retrieval pipeline in DocFlow is designed and visualized as a node link diagram. Create and modify information seeking pipeline is as easy as a series of drag and drop actions. Each node in the diagram is a functional component that performs data loading, retrieval, categorization, and visual analysis tasks. DocFlow currently supports 6 components, which can be seen from the Components panel. Zooming in, each component in the pipeline has 2 types of ports to accept the distinct data and parameters. Specifically, data ports are located on the left and right side of each component and are used to input and output document data. While visualization ports are located on the top and bottom side and are used to transmit visual parameters and which documents should get highlighted. Among these components, Document Explorer is the one for user to inspect the details of a corpus and also perform query-based document retrieval by typing in question format phrases or natural language questions directly. Document Mapper, on the other hand, presents the distribution of corpus on a scatter plot. User can use a lasso to select one or multiple groups of documents from the map and output it for further analysis. With the use of visualization port, one can highlight a selection of documents on a particular map. This is especially useful when clinicians have several articles that feel interesting and would like to explore more similar ones. Document Categorizer categorizes documents based on the answer they contained. User can check the answer keywords for each of the group and also export a specific group of articles for further analysis. Last but not least, the Flow Explorer shows hierarchical categorization result achieved by a series of document categorizer, where each column shows a categorization process, and each node on the column is a category with its height implies the size. The ribbons connecting consecutive columns reveal the relationships between categories. User can zoom and select the nodes when studying the categorization results. Next is an evaluation of the DocFlow. We first measure the accuracy of query-based document retrieval in 4 QA test datasets. We conduct and report the accuracy of extracting correct context from top 10, 20, and 100 most similar document embeddings based on the query. Our model achieves better retrieval accuracy in small retrieval numbers, especially in our target domain dataset, YAMER. We believe the superior performance is because we use Bellbird as our base encoders. We also conduct the efficiency analysis on a Tesla V100 GPUs. The result demonstrates scalability of our retrieval and categorization methods, and we can achieve near real-time inference for both operations. Next, we present a case study to illustrate the effectiveness of DocFlow. In the study, domain expert leverages DocFlow to quickly explore ADHD studies and retrieve publications to fulfill her research needs. After she uploaded the corpus, which contains 801 articles, she first categorized documents based on the population being studied, and she then selected children as population of the interest. Then she dived in the group and categorized them based on the treatment being applied. Among 4 groups, she chose mesopleniadate as the treatment of interest, and then categorized based on the compared groups and select the placebo as the group being compared with, and finally she got 10 articles. She then categorized 10 articles based on the outcome of the study and found that 2 studies reported significant improvement of the attention score in using mesopleniadate to treat children with ADHD. She also made use of Flow Explorer to check the distribution of the document among these 4 categorizers. One interesting finding our domain expert got is that by clicking the clozapine as a designed treatment, there is no study from the children category flow into it. After further research, she found that clozapine are reported to have several side effects on children and thought that would probably be the reason of me seeing such a flow. The domain experts are very satisfying with the intuitiveness and effectiveness of DocFlow. Lastly, we would like to quickly discuss the transferability and expandability of DocFlow. First, the design of DocFlow and the retrieval methods can be easily extended to other domains with proper model fine-tuning. For instance, one can replace BioBird with Scientific Bird if we want to apply DocFlow on scientific literature. Second, DocFlow is implemented with Vue.js and it is easy to embed more functional components for various new tasks. Lastly, we deploy DocFlow online and it is live at docscompass.web.app. We welcome anyone who is interested in to give it a try, and we are ready for the questions. Thank you very much for listening.